Welcome you all for this very important first session of the Indian Geotechnical Society IGS Annual Lecture, which will be delivered by Professor T.G. Sitaram. In fact, it's a personal pleasure for me to introduce him. Professor Sitaram obtained his BE in Civil Engineering from BTT College of Engineering, Davangere from Mysore University in 1983, Masters in Civil Engineering from University of Science in 1986, and PhD from University of Waterloo, Ontario, Canada in 1991, in the area of geomechanics. He was a postdoctoral fellow in the University of Texas, Austin until 1994, and he served in the University of Waterloo for some time, 6 months. He also served in various organizations like Bapuji Institute of Engineering and Technology, Davangere, Central Pollution Control Board, IIT Delhi, University of Waterloo, Canada, University of Texas, Austin, Yamaguchi University, and all of that. And in 1994, he joined in Institute of Science, and he's a senior professor in Institute of Science, and now he's on deputation to IIT as a director, IIT Gauhati as director. He's a founder chairman of the Center for Infrastructure, Sustainable Transport, and Urban Planning, and he received he was responsible for several research grants in that department, and he was also responsible for starting MTech and PhD programs in that particular department. And his areas of research include geotechnical engineering, geotechnical earthquake engineering, infrastructure engineering, rock mechanics, and earth ramp designs. He served as convener for developing geotechnical guidelines for seismic microgeneration, supported by National Disaster Mitigation Authority, NDMA, Government of India. His work on seismic microgeneration of urban areas, liquefaction analysis, and earthquake hazard evaluation in the area of geotechnical earthquake engineering has received worldwide recognition. And he's the chief editor of the International Journal of Geotechnical Earthquake Engineering, published by IGI Global, USA. He's also serving as a chief editor of Sustainable Urbanization Planning and Progress Voice Publishers. He served as ASC associate editor on for Journal of Materials ASC in Civil Engineering ASCE. And he's presently committee member on the Soils and Rock Instrumentation, TRB, and for the period 2007 to 16. He guided 25 PhDs for master's thesis per research and more than 25 ME projects. He has currently 8 doctoral students, and he has more than 25 research projects executed, and as a principal investigator, and also many international projects from European Union and German Academy of Sciences. He has served as a PAC on the program advisory committee of the Ministry of Earth Sciences and DST, and he's a PAC member of Landslides, and he has been a consultant on slope stability foundations for highest elevated bridge across Chenab for Mrs. Afghan, and it is, I think, more than 450 journal publications, and very high index of 24, and has so many consulting projects, 3 patents. The list goes on. I think he's a recipient of Gopal Ranjan Award of IIT Roorkee, and excellent contributions. Recently, he also got the Amulya Reddy Award in IISc in the field of sustainable development, and earlier he was the recipient of C.V. Raman State Award for Young Scientists. He's a visiting professor of the Rock Engineering Group of Department of Yamaguchi, and his list. He's incredible. I mean, we know as a colleague, as a friend, as a person, I know him very well, and it's a pleasure that it is my pleasure and privilege to invite him to deliver this annual lecture. Professor Sitaram, it's yours.
Thank you. Namaste to all. Can I share my screen?
Yes, sir, you can do that.
I think you can see my screen, right?
There is.
Honorable. Yeah, can you see the screen?
Yes, sir, it is visible. You can proceed.
Thank you. Namaskar. Namaskar. Good friend, Professor G.L. Shivakumar Babu, President of IGS, J.T. Sahu, Honorary Secretary of IGS, Professor CNV Satyanarayana Reddy, Organizing Chairman of IGS 2020, and all my distinguished teachers, friends of IGS, and the entire IGS community, and all my students, delegates of this 42nd Indian Geotechnical Conference, ladies and gentlemen. Very good morning to all of you. Let me first wish you all very happy New Year 2021. It's not very far away. It's only 13 more days. And also Merry Christmas to you. This year, people thought that is a washout because of the COVID-19, but really it has put us into a challenging times, but of course, all of us have come out very well. This COVID-19 pandemic has created a new order, and we are attending this IGC from our own offices, our home, and delivering all these lectures for a larger audience. Generally, we attend these IGCs regularly and meet all our friends. That's the occasion we are going to miss this time. But however, thanks to the technology, and I will tell you, we have leapfrogged using this technology by at least 10 years. If this pandemic was not there, we would not have done any of these, particularly going online, a total conference and many meetings and everything, you know. So thanks to the technology, we have adapted to the all this technology, even including all the senior professors are doing this at every universities. And I would like to take this opportunity to thank Indian Geotechnical Society for selecting me this annual lecture 2020. In this talk, I'm going to highlight our contribution in this area of geotechnical engineering in the last 25 years. The title of my talk, I put it, the quintessence of 25 years of our contributions to geotechnical earthquake engineering. As you all know, geotechnical engineering is a multidisciplinary area. The process of understanding and working with soil and rock, underground water, site and structural conditions in relation to the construction project emphasizes the role of geotechnical engineering in a broad way. A geotechnical engineer in his professional capacity plan, design the structures for buildings, roads, embankments, canals, and hundreds of other construction projects which are needed for the growth of the country. Beyond their construction role, the geotechnical engineer will also deal with the geological hazards like landslides, soil erosion, and in some extreme conditions, earthquakes and other areas as well. Many people ask me, what is this quintessence? The first known use of quintessence word in English dictionary, as per the Oxford Dictionary, was in the 15th century. Quintessence means the essence of a thing in its purest and most concentrated form. It also means the most perfect or typical example of a quality or a class. So we try to bring out good quality of work, what we did at Indian Institute of Science with my students, and today to present it to the IGS community. In our humble pathway to this, we have come across many hurdles, and even this pandemic is one of those. Long ago, when people believed that the nature was made up of 4 elements, earth, air, fire, and water, This is as per the, the British dictionary. They thought that the stars and planets were made up of yet another element. In the Middle Ages, people called this element by its medieval Latin name, Quinta Essentia, literally fifth essence. Quintessence means the fifth and highest element in ancient and medieval philosophy that permeates all nature and is the substance composing the celestial bodies, that is Akash. This is the dictionary says, this Oxford or Cambridge dictionary, if you search for the quintessence. But the Indian knowledge, it is much beyond this. If you go to Yajurveda, it says the 5 elements of life, that is nature, is made up of 5 major elements known as Panchabhutas. But the Panchamahabhuta are the 5 elements of the nature. According to Hindu mythology, every human body essentially are made up from 5 elements such as earth, bhumi, water, jala, fire, agni, air, vayu, and space, akasha. See, Indian knowledge was actually much before clearly defined the akash as one of the elements. I would like to quote Yajurveda, Tasmadva etasmadat atman akasha sambhuta akasha dvayaha vayor agnihi agneirasha adyab prithvihi prithviya vasadayaha vasadi bosnam annata prushaha. What it means is, from that Atman, supreme soul, space came into being. From space, wind, from wind, fire, from the fire, water, from water, earth, from earth, plants, from plants, food, from food, man came into being. So it's such a beautiful extraction. So in that context also, the earth is the key aspect of it, and geotechnical engineers who are dealing with earth for engineering purposes are also very important. So let me take you to my talk today. Let me first offer my thanks to all my teachers. I don't want to name anybody because I have a fear of missing someone, starting from the school days. And all my teachers, doctoral students, I had a very large number, 32 have graduated, and another maybe about 10 are working in both Indian Institute of Science as well as IIT Guwahati. And also thanks to funding agencies, received large funding from different agencies across India as well as outside. And I will also like to acknowledge all collaborators and research fellows who work with me. So some of the names of the PhD students working in the area of geotechnical earthquake engineering I have given you here. Since I joined my profession as an assistant professor at Indian Institute of Science in 1994 June, I got my master's in 1984, as our colleague said, and also PhD in Waterloo, and then came back to Indian Institute of Science in 1994. Since then, I am at Indian Institute of Science. Now I am on deputation to IIT Guwahati from July of 2019 as a director of Indian Institute of Technology, Guwahati. Let me tell you honestly, I haven't taken any earthquake engineering courses in entire my academic degrees where I earned. I never taken any earthquake engineering. I took this as a challenge as early as 95 when I joined as a faculty. And I first started to work on liquefaction of science. And I started doing that using numerical modeling, using discrete element modeling. And then developed cyclic triaxial testing at Indian Institute of Science as early as 1997. And at that time, I had only about 15 lakhs funded by DST, and I asked every company to, nobody was ready to give me that equipment for 15 lakhs. Maybe I underestimated it. And that time, my good friend, who is no more here with us, Mr. Jatinder Singh, offered to develop this indigenously in India. So jointly with HYCO, Hydraulic and Engineering Instruments, that particularly Mr. Jatinder Singh helped us, and he became a constant friend, not only to me, most of you, because he is the friend of all geotechnical engineering community. I think we are going to miss him this IGC. Otherwise, he generally never misses Indian Geotechnical Conference. Let me thank him also, and also give and pray Almighty to rest in peace his this thing, because he just passed away 2 years because of the COVID-19 itself. Okay. Focused on this particular topic of geotechnical earthquake engineering, when many professors asked me, what is this, geotechnical earthquake engineering or earthquake geotechnical engineering? Many questions were coming at that time, because if you remember, the first book on geotechnical earthquake engineering by Professor Stephen L. Kramer, the first edition came in January 7th of 1996. You can imagine now. 1995, we started working in this area. 97, we first got the cyclic traxel, first cyclic traxel equipment in the country. That too indigenously made. And we had a first project proposal also on liquefaction of sand based on discrete element modeling, but supported with some experiments from Government of India. So this is the background with which we move into my talk. The content of my today's presentation is very elaborate, but don't worry, I'm going to complete this in 1 hour. Very briefly touch upon the overview of what is just geotechnical earthquake engineering and what did we do in the geological, seismological, and geotechnical aspects of this. And then we are also, because quizzed by that, we need to also look at the seismicity and seismic hazard analysis to bring it to the ground level. Then we also developed our own ground motion prediction equations, site response, and the characterization studies for many projects, as well as many of the seismic microzonation studies. We have also extensively worked for the last 25 years on liquefaction. I'm going to highlight some of the work of what we have done. Then coming to seismic microzonation, we are the first one to start a microzonation project after Jabalpur in Bangalore. And then many people had a question, why did you choose Bangalore? Because I was there and it is easier to do in Bangalore, so we took the challenge. But we learned a lot of things there. You see, please understand, the effect of soils is very, very key, and we learned. And now recently we moved to time frequency analysis in seismic studies, and then seismic design of geotechnical structures. Many projects I've involved both internationally and nationally, where we have adopted our design, and then experimental and numerical methods and dynamic behavior of soils, shock and blast loading on the granular materials, which is again a very unique work, which is first of its kind, where we have used the shock waves, so which are almost more than the speed of sound. The wave velocities will be more than the speed of sound. Then after doing all this work, I realized what we need to do is something on educate the masses on earthquake preparedness, and contribution on developmental facilities, what we have contributed over a period of time, and also my outreach activities briefly, and conclude my talk. So mitigation of earthquake problems with emphasis on subsoil liquefaction and local site effects is my topic today. And studying the features of earthquakes induced geotechnical damages also I will highlight. Friends, all of you know that earthquakes occur in well-defined belts that corresponds to active plate tectonic zones. So you could see there in this picture, major 7 plates. The constant bumping, grinding, and lateral movement along the crustal boundaries can create sudden movements that result in earthquakes. This is a basic definition for an young engineer to understand how the earthquakes are created. So once each of these 3 types of plate boundaries, okay, there are different plate boundaries like convergent, divergent, transform boundaries, has a distinct formation or a pattern of earthquakes which can create it. You can see the ring of fire which has been shown on the slide here, okay, The red dots are basically the earthquakes, large earthquakes which happen, which is generally happens at the interplate between the Eurasian plate to Indo-Australian plate, or Indo-Australian plate to North American plate, between that plate, because of the movement of these crustal boundaries which created the earthquakes, and those are the earthquakes which are measured. And you can see the circum-Pacific belt, which is what we call ring of fire, follows the rim of the Pacific Ocean and hosts over 80% of the world's earthquakes happen in the ring of fire. 80%. So then, and also 100% of all the deep earthquakes happen only in the Pacific plate, around the Pacific plate. Other earthquake zones are the Mediterranean and the Himalayan belt. This is the belt. You don't see dots here. I will tell you why it is not there. When you closerly look at it and look at very large earthquakes, then we will see some more very carefully. So other earthquake zones are Mediterranean, Himalayan belt, as I showed you, just north of India. And also the bottom of the world's oceans. So distribution plots in this plot reveal that many earthquakes are associated with either the volcanic action or the oceanic trenches or the interplate, the earthquakes over subduction zones in the circum-Pacific belt. So there is a great interest in learning enough about earthquakes. So to be able to predict their occurrence and possibly even control them. The probability of an earthquake striking an area can be calculated based on the historic seismic activity in that area. Repeated patterns of earthquakes make it possible to predict when the next one might occur, not maybe the exact time and the exact place, but probably you could identify what is the return period of these earthquakes. When rock masses suddenly move deep within the earth in response to tectonic stress, energy in the form of seismic waves moves outward through the rock. That means seismic waves actually travel when the movement occurs at the focus. The initial movement is generally at the focus, and the waves move outward through the rock from the point of origin called the focus. There are three types of seismic waves: P, S, and surface waves. Among them, surface waves are the slowest seismic waves and travel outward on the Earth's surface from the epicenter, much like ripples to form a stone. When you throw a stone into water, the ripples form, almost similar to that. These surface waves travel on the ground. They create most of the damage at the surface because they are the waves that produce the most ground movement and pass through an area the most slowly. So what you are seeing, the top two pictures, either in the 2005 Kashmir earthquake or 2015 Nepal earthquake, is the damaged building. The picture clearly highlights the importance of geotechnical earthquake engineering. Why? Because you have to see the bottom picture in connection with this. See, assume that these are some of the structures which are there on the ground, founded maybe on a pile foundation or a shallow foundation. But what happens when an earthquake comes? Waves actually travel through, different medium and reaches to the closer to the foundation, and in the foundation they started moving vertically, and these waves actually will be dependent on many factors. What could be the dynamic soil structure interaction, building model, soil constitutive model, interface boundary model, or the seismic ground response analysis, all of that. So what you see is only the top structure is collapsed. And so far, earthquake engineering were focused on that to find out how to reduce. That is definitely an engineering of the structure is possible. So even though solution lies in buildings, it is better for us to understand how these damaging waves travel through the ground, and is there any way we can reduce their effects on building? That is the question of geotechnical earthquake engineering. I'll repeat that again. It is better for us to understand how these damaging waves travel through the ground, and is there any way we can reduce their effects on buildings? That's the objective of that if you can understand the wave movements and also can modify the ground below these structures to take these kind of waves, and that is the challenge of geotechnical engineer. And that is the role of geotechnical earthquake engineer in particular. So let me take you to the India. As I told you, this is the plate boundary between Indo-Australian plate and the Eurasian plate. See, that's the Himalayas. Even recent measurement of both Chinese and Nepalese showed that Himalaya is rising. That is because Indian plate, which is situated in Indo-Australian plate, is moving in the northeasterly direction at a rate of 50 millimeter per year. And recently, they have also clearly said Himalaya is in the height has increased. That means because of the both collision, Himalaya is rising, which also creates many large earthquakes. So the earthquakes, what has been given at the boundary of the plate, either main boundary thrust or main central thrust, the location, year, and number of fatalities clearly shows here. See, whether we start with 1934 Bihar earthquake, 8.1 on Richter scale, and also you see the number of deaths which is there, and see, almost like 15,854 people died in Bihar earthquake, and Assam earthquake only 1526, when magnitude is much higher. Because if you look at where is Assam earthquake has happened, see, one was in 1951, was actually in the north of Assam. I'll show you the next picture. And one was at the Meghalaya. That was the 1987, I think. So these earthquakes, what this picture says that clearly you see there is no relation between the magnitude of the earthquake and number of deaths. See, number of deaths in a 6.4 earthquake of Maharashtra, Latur, was much, much larger. Why it is so? If you ask this question very fundamentally, earthquakes are not disasters. Earthquakes doesn't kill people. It is the buildings. So that's where, you can clearly see even a smaller magnitude earthquake, which could demolish many of the buildings. When the people are sleeping in those buildings, you will have the disastrous effects. So there is no way much except the geotechnical engineers can do to control these wave movements, which is coming to the building. There is no way. The structural engineers are only worried about how do you design for these waves. But we at least try to control its effect. That's the role of geotechnical earthquake engineer. So let me take you to, again, very closer view of the India, that is the plate, where India is hitting the Eurasian plate. And when you look at this, the seismic gaps are clearly visible. This is what we call central gap. That is, the potential earthquakes are 8.5 magnitude, but we think that there was an earthquake in 1505, but we do not know exact record of that. That is the oldest record. If you see, that means we do not have even a 300 years of a record for a civilization which is 5,000 years old. And we have only the records for only last 300 years. We claim to know more about earthquakes, but very, very sad state today that if you look at 1934, this is the Bihar earthquake, and I promised you that is 1950 Assam earthquake is in the northeast, the very far away at where Dibrugarh. That's where the depression of Brahmaputra is taken, almost 3.5 meters. 1947 earthquake was in Meghalaya, okay, Shillong. And then if you can see, these were the gaps where there are not many earthquakes have happened. Central gap and East Bhutan gap, 8.7, okay. So what do you mean by these seismic gaps? The seismic gaps are stretches along an active fault zone that have not produced earthquake for a significant time. Scientists believe that these gaps may be extra resistive areas along the fault where strain is being stored in the fault blocks and where earthquakes will likely occur when the strain is finally released. An earthquake beneath the ocean results in a huge waves called seismic sea waves that devastates the coastline. That is what we call tsunamis. You must be remembering 2001, 2004 tsunami, Sumatra earthquake, which has caused the tsunami, which affected India as well. Scientists who study earthquakes, were basically seismologists, but now we are also, all engineers are also getting into this business, because so we need to bring that whatever understanding about earthquakes and how they cause and how they travel, the waves travel, and then we need to track that to the base of the foundation, and then our structural engineer friends will talk about how we need to build design these structures. So it is better to understand from the beginning. That's the attempt of our group at Institute of Science, starting from the cause of the happening of the earthquake to the moment of these waves, and then properties of the soils, how they change with the waves, and then estimate, and then take it to the ground level and give it to our structural engineering friends, so that design earthquake, so that they can design these structures. So it of hope to eventually, even our seismologist friends hope to eventually predict earthquakes, but I think the science of prediction is very far away. Engineers are actually more challenged to develop the new designs that will enable buildings to withstand the forces of earthquakes. So that's where the role of geotechnical earthquake engineering becomes more important, so that how to contain the effect of these waves reaching to the foundation of our buildings, so that we can save these buildings in a very effective way. So even with the seismic design codes and advanced construction practices, recent earthquakes like the 7.8, the Gorkha earthquake in 2015, have caused large losses to life and property, which is nothing in Nepal, which has happened. Fatalities around 9,000, injuries about 21,000, financial losses over $10 billion reported in the Nepal earthquake. Okay. So the major earthquakes in India and adjoining regions I can show you, and again I would like to highlight to you, there is no correlation between the casualties and the economic loss with the magnitude of the earthquake. That clearly spells that earthquakes, doesn't kill people. Earthquake doesn't kill people, the buildings do. And buildings, and I modify that, buildings and foundation. I'll come back to that again. So the number from the table, basically the previous table, advocate the need for updating the current knowledge and the construction practices in need to curbing these losses. The knowledge of earthquakes, its processes and dynamics have to be continuously kept in the limelight of research, because this is not going to be, okay, I've done the analysis, it's not over. Things will change when there was a new earthquakes and new data is available to us. And new faults are also can be created because of earthquakes. So the geotectonics also can change, because our plates are moving. So influence of local geotechnical and geological and topographical conditions are most key aspects for understanding and designing our structures, so that we can reduce disasters. Okay, so geotechnical engineering plays a major role. Further, construction practices in seismically active areas need to be revamped with proper codal provisions and provisions for local site effects, and strict enactment of these provisions during construction is necessary. So secondary effects of these earthquakes are tsunamis, soil liquefaction, fire, disease and famine, landslides. And in that, the role of soil mechanics again comes into, in a very big way, is understanding of soil liquefaction. Okay, what really happens in soil liquefaction is, please understand, below the foundation, the water which was there, because the kind of earthquakes magnitudes are less than a minute, 40 seconds, 50 seconds, dynamic loads, even in a very permeable sandy medium, the pore pressure can shoot up and make the effective stress zero, and shear strength becomes zero, and sand starts flowing like a fluid. And then the liquefaction will occur. And it can also come out with sand boiling, very similar to what we have seen in earth dams, and the buildings can sink. But what happens to the pipelines and sewers? So they actually float because of the buoyancy effect. So, and lateral spreading also of the ground can take place. So these are some of the effects of the earthquakes. Please note that earthquakes or tsunami or volcanic eruption are actually commonly categorized as disasters. They're not disasters. They are basically what I call them as hazards. Why I don't call them as disasters, I'll tell you in the next slide. If a major earthquake shook an inhabited land like Greenland, there were no fatalities, no building collapsed, because there are no buildings itself. So no public service disrupted. Otherwise, the impact of the hazard is not disastrous, even though it may be a 9 magnitude earthquake there. So then the earthquake is not very likely to be considered as a disaster. So earthquake is an hazard, not a disaster. It becomes a disaster if it hits the habitat or a very densely populated area. People. So the people and hazard coming together makes a disaster. So when I say people, it is also buildings where the people used to stay. The effort should be to mitigate and prevent the disaster, and also an attempt to reduce the risk. So far, the structural engineer's role was to reduce the risk in the buildings, but I am saying we can also do something at the ground level. How one can actually minimize the risks, and at the end, what really matters would not be the emergency response after so many lives were taken. See, we have done a fantastic job creating National Disaster Force in the NDRF through NDMA. But that is all beyond after the earthquake occurs and after the people are killed. It is only an emergency response, which is also very essential. But however, how to secure the lives and properties from the hazards, that is what I call engineering preparedness for a country like ours. We need to do a lot. We have to prepare not only from the engineering point of view as a civil engineers, we have to also prepare the community as well. That's what I'm going to focus on, both preparedness for the community and preparedness for the engineers. So that's where the role of geotechnical earthquake engineering comes into picture. Very young discipline that considers the geotechnical aspects of the wider discipline of earthquake engineering, involves aspects of geology, seismology, geotechnical engineering, and risk analysis, leading to an assessment of earthquake hazard and restrain the associated risk to endurable limits. Geotechnical aspects like surface topography, local soil and site effects, soil type, along with seismological aspects like the frequency of incident wave, influencing the maximum acceleration experience in the ground, evaluation of ground motion at the ground level for mitigation of earthquake hazards, and this demands a meticulous research and new development in these areas. That's where our work has caught the eye of the storm. Secondary effects like soil liquefaction, as I told you earlier, landslides and tsunamis are also common too. The geometry and material properties of the subsurface soil, the way the structures within the ground are also key. That means we need to understand what are the kinds of structures below the ground before you put in the foundation. Its stratification and its properties of the bedrock ground motion have a substantial influence on the site amplification and local site effects. These effects were witnessed during the infamous Niigata, Mexico, San Francisco, and Bhuj earthquake over the years. It is not a new thing. Even the picture what I've shown you is the soil liquefaction due to Christchurch earthquake in 2011. Look at 6.2 on MW scale, but look at how the sand has become almost like a fluid. So the entire car has gone down. So this is what we need to understand what really happens. So let me give you some definition of the local site effect. What do I mean by local site effect? See, when this bedrock, when the earthquake, created there, and this is the time history of a wave, okay, the amplitude versus time. And then if you hit the sediment, it amplifies. If you measure, if you put two instruments, one at the bedrock and one at the top, the sediment clearly modifies the incoming wave, and the characteristics like amplitude of the wave, frequency of the wave, and duration also will change. What is causing that change from here to there? Not just the distance. Actually, if it is distance, it should have been attenuated. Why what is amplifying? The amplification is because of the soil characteristics and also due to sometimes topography or the structures within the ground. So this needs to be understood. Wave amplification in sediment layer and wave amplification due to local topography needs to be understood very clearly. But please understand, to understand the local topography is a very great challenging. Even today, we do not have answers. So we have done some progress in at least in the sediment, how the sediment responses. Influence of local geotechnical, geological, and topographical condition is the key. And if you can assess that, and then we can try to modify that, see how these waves will modify. So whether we can reduce the effect of these waves even before reaching the foundation. Because please understand, in civil engineering, our scale is in the 100 meters, less than 100 meters. Nowhere we will put foundation more than 100 meters, nowhere. So our interest will be completely in the top 100 meters of the ground. Okay. Even for a Burj Khalifa, the foundation is only at 55 to 60 meters below the ground. Why I took Khalifa, Burj Khalifa is about 830 meters tall above the ground, but below the ground, it is 55 to 60 meters. So the geophysicists study how these waves travel in kilometers, but our job, geotechnical engineers' job, is to study how these waves transmit in the top 100 meters of the ground. And that also we are unable to do with the kind of investigation capabilities we have today. None of our, in Delhi microdonation, we were unable to drill a deep borehole. It doesn't mean that we do not have the capability of drilling. See, our own country in petroleum engineering, in the search of petroleum, we have drilled 7-kilometer borehole. But we are unable to drill about 120 meters in Delhi. So there are challenges actually, because this is also because of the practicing people, geotechnical practicing people. So the amplitude and duration of ground shaking at a specific site depends on different factors. That is energy release of the earthquake event, depending on the rupture size and type, directivity of the energy release, depending on the orientation of the rupture fault, distance from the site to the earthquake source, geological conditions between the earthquake source and the site, and local soil condition and topographical conditions. All of these will affect the typical configuration that cause side effect is, you can see the features present at the Earth's surface have also been identified as having an influencing and shaking intensity. The building sitting on a sediment, horizontal sediment response will be different. When it is sitting in a valley, it is different. And the crest of the slope, it is different. And this kind of a two path when the waves are following would be different. So some studies of the distribution of the intensity of shaking experience in an earthquake concluded that hilltop sites often shook at one intensity level higher. You note that one intensity higher than the nearby sites with flatter topography. So many factors are going to affect. Studies on the influence of soil condition and strong motion is a very recent phenomenon, friends. It's not a very new area of research. As late as the Guro earthquake of 1985 started the storm studies of Mexico City. It doesn't mean that we didn't know about soil are going to affect the waves movement. Historical reference to local site effects extend back to nearly 200 years. But somehow, geotechnical engineers were never involved in earthquake engineering because they thought it is not our job, it is only structural engineer's job. But now we realize that it's more important to understand the ground where you put your foundation. Spitak earthquake 1980, Armenia, Loma Prieta has really given us a lot of understanding about liquefaction. And Kobe earthquake, and where coastal areas, many of them have liquefied. Kocaeli earthquake in Turkey, and Erzincan earthquake in Turkey, where resonance is the other. Buj earthquake also showed a large number of liquefaction areas. But luckily in Buj earthquake, it happened in an area, a lot of liquefaction has happened in an area of a no man's land in the border of India and Pakistan. So we didn't see serious effects of liquefaction there. So historical reference to local survey extend back nearly 200 years, but did not appear in courts even in 70s, 80s, and even today, even some of our courts. So damages due to local side effects and liquefaction in earthquakes, you can see many of them you can relate it to geotechnical engineering aspects, the effect of subsoil, below the ground, below the structures, or the cars. So if you had really knew this and if you can modify that ground, you could have saved many of these structures. Okay, so that's the emphasis of this. And even today, we have not yet understood. So how do we really reduce these impacts of these earthquakes? What is the knowledge of geotechnical earthquake engineering which is required to do this? So as you, again, I will repeat, earthquakes don't kill people, that is buildings do. Because I give you an example of 1994, two earthquakes. One is the San Francisco earthquake, which is also something like close to 6.2 magnitude in the MW scale, or 6.4. And the Kilari or Latur earthquake, which is also 6.4. Both happened in the midnight. Okay, close to midnight or the early morning, 3 o'clock. So when in Kilari, there are so many deaths, 15,000 plus, and then large number of Y with a small magnitude earthquake, because people were sleeping in their unsafe houses, in the fragile buildings. But the same people in San Francisco who are sleeping in safe houses. Imagine if that earthquake of 6.2, because the period was longer there, many bridges actually collapsed. You could have been counting large number of deaths in San Francisco earthquake if that happened in the morning time, because traffic would have been very high. Okay, but they were sleeping in the French, so the number of deaths were almost nil or maybe 1 or 2. So many deaths and injuries in earthquake result from collapse of structures. Solution lies in buildings and foundations. That's the theme of my talk today. The foundation is the very key, and not in the earthquakes as such. Why I said that is, very little you can stop an earthquake coming. Okay, it is only a complacency, you can forget about it, but not really you can do much about earthquakes. So our ground should be engineered to transmit less vibrations to structures, and structures should be designed to withstand the vibrations. So both are important, ladies and gentlemen. So far, our friends have done fantastically well in structural engineering above the ground, and even maybe at the junction of the ground and the soil. But below the ground, there is a lot we can do, because ground improvement is the key. Many of you are all working in the ground improvement area, and ground improvement is the key here. Evaluation of hazard, considering the local soil effect, which is a ground, improved ground, is the key. Then we can actually bring down the hazard, and then automatically we can design much better. This is the challenge, actually, even I highlighted for the Sri Ram temple at Ayodhya. So recently, they made a committee. I said, we can improve the ground below that, because it's all unconsolidated alluvium sediments. Coming to the geometry of the subsoil structure, which we can do much, we cannot do much, but we need to understand that. How do we understand the geometry below the ground? So below the ground, what is the kind of geometry we have? What kind of unconsolidated sediment is there? It is the role of the geotechnical engineer. Characterization of the ground is the key. The role of geotechnical testing agencies becomes much more valuable. But considering the state and affairs of the geotechnical testing in the country, this is a very, very challenging job for all of us as a community who have come together, because only one community which is very well together in India is the Geotechnical Society, which has done a fantastic job. So this we need to translate, not only in educating the academic people and the students and this thing, we also need to educate the consulting and the companies who do the investigation, bring up their quality. So we need to characterize the ground very much more accurately, much more elaborately, which can reduce a lot of damages. So geometry of the subsoil structure, the soil type and the variation, the properties with depth and lateral discontinuities and the surface topography, which influence the amplification of ground motion and hence the intensity of damage during the destructive earthquakes, has to be done very effectively and efficiently. The tests, not much changes, ladies and gentlemen. You know all of that. See, look at the laboratory tests. We do that, but we don't do seriously. We don't do it correctly. So we know all of it. There is nothing really out of the box we have to do here. Grain size, Atterberg, natural water permeability, strength. But as we all said, and all our teachers have told us many times, geotechnical engineering, even though it's a science, its practice is an art. So we need a lot of involvement in understanding the ground and its properties. So we need to study their reports properly, understand who has done that, how they have done it, and what is the results have come, and validate back and forth with the different techniques. So field tests, all are again known, except some of them which are come into the industry, multi-channel associated waves, spectral associated in the last 10 years. Otherwise, these are all existing from last 40, 50 years, because geotechnical engineering is also coming to almost to 100 years of celebration, after Carl Tarzagi has given the name of it. So field tests, again, coming to suspension logging, all of these were there, nothing new. What we did is we tried to develop some of the work. I will highlight these things a little later. We have developed a piece of vibrocone where we can actually calculate the liquefaction resistance in the laboratory as well as in the field. And we have also, as I told you, this is cyclic triaxial test, thanks to Mr. Jatinder Singh, HICO. We have developed this and he has sold it, maybe 15 to 20 of them across India as well as Iran and some other countries, even outside as well. And we have also developed a shake table at Institute of Science very early. And this is the laminar box which we created very early. And a lot of students and faculty got benefited through this. Let me come to the hazard. As I told you, why I'm looking at hazard, because I want to estimate the hazard considering the soil below the ground. So unless I estimate myself the entire thing, I cannot translate to the ground. So this is where, when I started, many people asked me, why are you doing this? This is nothing very innovative. But unless we bring that values and numbers to the soil bed and then translate, so we cannot take somebody else's results and put it here. So we started looking at the hazard analysis, so which is very standard. That is the deterministic hazard analysis, probabilistic hazard analysis. I will not go into details of these. Some of you are interested, either you can see our books or our papers. So there is a quantified levels of ground shaking. Design and construction practice are to be defined for the particular site to ensure seismically safe structure. So that's the objective. These are some of our books. So earthquake hazard assessment, which will tell you, delineates both the deterministic as probabilistic, and also seismic zonation at different scale levels, at a city level, at a specific site level, and at a nation level. We have done this very, very categorically. Several PhD students have contributed to this. This is both in Springer, this is in CRC Press, and this is in Springer. And lastly, I told you, I've talked about the preparing for earthquake lessons for India, wherein I will also highlight this about this book a little later. But here, what I've learned is we need to also prepare the community, prepare the engineers, so that there is something you can do to the ground. It is not just the buildings. It is the ground also has to be improved below the buildings. That's very message which I wanted to take it through this today's talk. So the ground is, this is the book which we did for the NDMA, Geotechnical and Geophysical Investigation for Seismic Resonation Studies of Urban Centers in India. Again, thanks to many who have contributed into this. So where our book delineates the data collection to homogenization and declustering of events through seismic source characterization, seismicity analysis, and identification of attenuation relationship. This is very important, particularly when it reaches the ground and soil layer, how this attenuation will translate into amplification. Okay. So otherwise the waves would be attenuating over a period of time, rocks and soils of some density. But once it sees the loose soil or a material which will amplify, how does this happen? Hazard evaluation is very key, both from the deterministic, probabilistic, considering the geotechnical and geophysical investigation for microzonation. So as I told you, this is the area where we have received large number of earthquakes, and 15% of the great earthquakes have happened in the 20th century along this plate boundary. But there are gaps, as I showed you earlier, and so far Assam earthquake in this region is the 8.57th largest, but I showed you also very few people killed in that area because it happened in a very remote area when Northeast was not so much habituated. But if it happens today, there are large dams also there we are constructing. So we have to be very careful. So major earthquakes are at plate boundaries. There are earthquakes intraplate like Latur and other things which are on a known or unknown fault. And Bhuj is also on a fault. So please remember, these are not actually the plate boundary earthquakes. These are the plate boundary earthquakes. So we have done a very detailed analysis considering many zones. We have identified regional seismic zones. So there are more than 100 also we have taken. We have taken 5, 6, 10, 15. Many students have done. So I'm not going to go everything here, but Kolatayar has done a significant work for the entire India. And that was about 104 or 105, 120 or something, zones we have considered, and we have calculated probabilistically as well as deterministically the peak ground acceleration, considering 10% probability of occurrence in 50 years. So this is where I would like to tell you that now the new temple, what Ram temple, what they are planning to build in Ayodhya, the life of this should be 1,000 years. That means we need to modify this 50 years, because in engineering, generally we do either 50 years or 100 years, or some of the nuclear power structures we might go to 300, 500 years. But we haven't really designed for 1,000 years any structures. Nowhere, not only in India, anywhere else. So we have also, because of the uncertainties are many, so we have also used a logic tree approach. In the earlier days, we didn't have a proper attenuation models. We have chosen many attenuation model, weightage factors for them. This is what is logic tree, which gives you an option to weigh the, okay, this may be better, this may be better, all these concepts and linear sources, aerial sources, point sources, all kinds of analysis we have done. Our book actually highlights that. What is the objective? Finally, we want to get the spectral acceleration versus time period, at the base of the foundation. Okay, so we have also done that, verified it with so many researchers before taking it to the ground. So now coming to the ground motion prediction equations. See, as I told you, we didn't have ground motion equations in India for generated for Indian region. So we used to adopt all the Western ones. Oh, they are similar, and all these kinds of reasoning we used to give. And very early days, one researcher had done with synthetic things. We thought that is the final thing. But finally, what we have learned over a period of a year, we can do that very effectively. Our students have demonstrated exemplifiedly, fantastically. So these GMPs are basically empirical equations to estimate the level of ground movement during an earthquake event at a particular site, considering the influential source and event parameters. The influential parameters are the event mechanism, site characteristics, properties of the propagation of path, and local soil and site geology. Recorded ground motion data is the one key. So we started with Anbalagan. His contribution is significant on microzonation and many other area. And I'm very happy that he's continuing his work and at our Institute of Science. Simulated the synthetic data. Very early, he used the simulated synthetic data for Lucknow along with our students. And purely, now we are talking about in 2020, purely recorded ground motion data. That is, Ramakrishnan and Srivalsa has contributed exemplifiedly on to develop new GMPs, ground motion prediction, actually, based on the actual data. That's all I'm going to show today. I'm not going to show you all other what we have experimented earlier, because there is no time. So this is the basically, our new GMP, what we have developed. We have also compared with various GMPs. And what is interesting is we wanted to calculate 300 kilometers away from the epicenter. So that we can use this for a region like Indo-Gangetic belt, where the side effects would be almost close to about 300 to 400 kilometers away. So seismotectonic, this is the work of Ramakrishnan, which is very new, map of north and central Himalayas, and also northeast Himalayas, showing seismic sources and recording stations. See, here we have used a total of 33 earthquake events with a total of 278 data entries in the north and central Himalayas. These are the Himalayas, and these triangled one are the recording stations. The events considered 4.2, 7.8. See, please note that there are not many major earthquakes. It's a complacency built in so that our people are not ready. Any large scale earthquake, as I showed you earlier, 8.7 earthquake can hit this area. When we do not know, it might happen tomorrow even. That's the kind of thing is there. We do not know exactly when this kind of earthquakes can occur. Hypocentral distance of 16 km to 1560 km was available for north central Himalayas earlier. So we have developed these new attenuation relationships or ground motion prediction equation. Even for Northeast Himalayas, based on 25 earthquake events with a total of 210 data entries, ranging from moment magnitude of 4.2 to 6.9, central distance of 42 to 640, which has already been published in the Earthquake Engineering Journal. So these are the original recorded data of Nepal-India border earthquake of April 4th of 2011 was put on this. See, very good correlation with our new GMP, what has been developed. Okay, this is for the North and Central Himalayas. This is for the Northeast Himalayas. So we are also very good prediction. So we are quite happy with that. We can develop based on the actual measured earthquake data. A new GMP is being developed for both North and Central Himalayas and also Northeast Himalayas. So then coming to the site effects, this is the story I'm telling you. Once you do this, bring the bedrock motion too close to about 100 meters or 50 meters below the foundation, look at the soil below the foundations and understand the site effects. That's the challenge of the geotechnical earthquake engineers. And characterization, ground characterization plays a major role. So for a comprehensive site response assessment, micronization, subsurface characterization, considering subsurface profiling is very essential. And understanding of the site soil behavior and response to seismic loading is necessary to assess and mitigate the hazards due to earthquakes. Evaluation of aftermaths of the earthquakes has shown that the intensity of ground motion is directly related to soil stratification. So, what I would like to show you here is, see, we have made the amplification map of Bangalore, and that is directly correlatable to VS30. That's the shear wave velocity at up to top 30 meter, average shear wave velocity in the top 30 meter. And we have also commented on that, whether 30 meter is essential or only soil is essential, or we need to average soil and rock within the 30 meter. All that, a lot of papers are there. One is interested. We have asked fundamental questions on how one needs to calculate. But in general, for a 30 meter VS30 still works for most of the sites. But for some sites, we have to deviate that, like cities like Bangalore and other things, where shallow bedrock is available. So coming to site response, studies have been carried out based on SPT, CPT, MSW test data, where shear wave velocity is directly measured here. Here, shear wave velocity is calculated based on N value or N correction value. So again, lot of experiments we have done, corrections, how corrections should be applied, whether corrections are required or not. If you don't believe in N value, what our companies, geotechnical companies give, then what is the use of doing all these corrections? Also question came up. Many questions we have posed ourselves and finally felt that a shear wave velocity profiling is very essential for seismic micronization. Very, very important MSW, and definitely we would like to do something SPT because we want to see the samples below the ground, how they are in what stage, which is not possible through the shear wave velocity. So even though geophysical has given a fantastic opportunity to understand and create the ground below what it is, and also see below the ground without disturbing the ground, but looking at the soil is very, very important. Very important to understand, feel that as a geotechnical engineer, you have to feel the soil, whether it is a clay, whether it is a sand or a silty sand, very important. So we have also during this, the innovations have come at, we have created 3D subsurface profiles for city of Bangalore. So we can use it for many new projects, which is coming as an initial investigation, very fast one. But again, that has to be verified. So we have given it to Bangalore Metro, we have given it to monorail, many of those data what we have collected in 3D subsurface profiling. Extensive field and laboratory tests were also conducted, and thanks to all my students. See, more than me, as I told you, I never took an earthquake engineering course, but our students have really worked very hard, and site response, amplification factors with all different kinds of model, with the deep, shallow, all that they have done, liquefaction and mud flows, ground subsidence. So this is, we also gone into Northeast. Other than Lucknow, one student did in Lucknow, Professor Abhishek, and then Professor Arjun Shell is at NIT Silchar, who did it on Northeast, because he comes from here. He went to Mizoram, he went to Tripura. A lot of work has done based on geotechnical testing for Mizoram and Tripura, and SPT, MSW test site. And they have classified the mean design response spectrum was evaluated at the bedrock. Surface levels were developed, and compared with that of the Indian Standard Code, driving to the conclusion that zone factor recommended in IS codes are underestimated. In many, invariably what we found, what you assess the ground response at the founding level of foundations, invariably underestimates by IS 1893. Okay, and wherein very important to do the site specific. The issue of site response, even today, our codes are very, very weak. Please remember, only Eurocode has done reasonably better considering two different magnitude of earthquakes, larger than 5.5 MW and less than 5.5. Soil classification A, B, C, D, E, 5. This is the Eurocode is much better, covering an entire range of shear wave velocity. But look at the Indian code, we are still with 3 types, rock, medium, and soil. Even the 2016 also is not changed. Ground motion in terms of response spectra for each soil class is very important to evaluate. 5 different classes are generally used in the Eurocode, supported by strong motion data. These are all supported by strong motion data. Please understand that. So it's very average VS30 I talked about earlier, still valid, and you can use it for most of the sites. For some sites, we might have to modify. Let me come to the liquefaction now. Soil tends to flow like a viscous fluid, as I showed you earlier in several pictures, which causes significant drop in soil bearing capacity and induces failure due to settlement in the structures. Bridge and building foundation failure. This is actually after Professor Madhabushi, Gopal Madhabushi from Cambridge. And you can see that 2001 Bhuj earthquake. So a typical scenario of soil liquefaction in India was witnessed during the 2001 Bhuj earthquake with a magnitude of 7.7. So this earthquake, luckily, most of the liquefaction which has occurred in the remote areas, I told you, in the border of India and China. So even today, most of the international agencies, or all agencies, use the very simplified approach of the Seed-and-Idris, and this is the methodology. That is, whether the cyclic stress ratio is above this curve, and then it's liquefaction, and below no liquefaction, and these are the procedure we follow for a liquefaction hazard assessment. Okay, but please remember, liquefaction is, and I have to tell you, CITIN has gone very, very carefully looking at very finer things, but I don't know whether it's really required, because many times it's a very complicated equations you generate, but it's not applicable. Cyclic resistance ratio is estimated, and then magnitude scaling factor for because it's only designed for 7 earthquakes, and then 7.5 magnitude, and then you scale it for other earthquakes. So generally, magnitude 5 and above only can cause liquefaction, and only in the top 15 meters or so. So evaluation, what we brought in through our student is there are a lot of uncertainties in this testing. So it's better to also do probabilistic liquefaction potential. So some of you are interested, see our papers on probabilistic liquefaction potential to account for the uncertainties in a better way. A probabilistic performance-based liquefaction potential needs to be evaluated at a first level, as a first level. I'm not saying that is the final level. Final level, we can do site-specific based on Seed-and-Idris as well. So here, I would like to quote some of the work what we have done on the with Anbalagan on the response of overlying soil to evaluate the amplification and liquefaction potential of the city of Bangalore, and wherein we brought the assess of site amplification response, bedrock level PGA estimated in the past studies, SPT data, and other geotechnical information, and synthetically generated ground motion was also used. And then later on, we modified that to develop a 3-dimensional subsurface model, as I explained earlier to you. Using this model, a preliminary liquefaction susceptibility map was generated based on Seed-and-Idris approach, and then modified using the probabilistic approach later on. Okay, that is with a written period of 475 years in Bangalore Urban Center by Vipin and other colleagues. So let me come to micronization of my work. A lot of my work was on micronization. I've started in Bangalore in as early as 96, 97, and then moved on to Lucknow city, and then I was also involved in the Delhi microdonation of the both scales. One is to 10,000 and also the larger scale. So basically what is zonation is, seismic zonation is the practice of subdividing a region into a different categories of zones based on various geotechnical, geological, and seismological parameter for effective use in land use planning for earthquake effects. Please note that seismic zonation plays a major role in many decision-making process. It is not just for evaluating the hazard. It is can be used in emergency response and deputing emergency response to certain area also. So these maps, see, in California, people used to even, where do I buy next property? So that's the level at which it is reached. So very important. Today, the zonation maps are used for insuring your buildings, structures, whatever you are doing. So there is a lot of importance to it. But thanks to the Government of India and through our efforts, we are able to push this agenda to convert through the PAC, saying that India has taken up 64 cities for doing macrozonation. Please see the challenge. Challenge is awarding contracts to geotechnical engineers to become a bottleneck for them also. So that's what we have to come out of that. We need to really generate. I request the Honorable President of the ISMGE to really give more focus on the geotechnical testing in the international level. That's not done. See, we do good geotechnical testing in the offshore because we put in a lot of money there. But onshore, whether it is America, whether it is Japan, the quality of onshore against offshore is always difference. Okay, because offshore, when you go, you will only get one time to do that. So they do it very carefully and spending a lot of effort and collect a lot of undisturbed sample, even in the difficult environment. But onshore, we don't do that much more effectively what we do in the offshore. So anyway, macrozonation basically is a subdivision of the region into zones that have relatively similar exposure to various earthquake-related effects. This exercise is similar to the macro-level hazard evaluation, but requires more rigorous input about the site-specific geological condition, geotechnical characteristics of the site, ground response of the soil column to earthquake motion and their effect, ground conditions which would enhance the earthquake effects like liquefaction of soil, groundwater condition. Why I have put all these? To show that to the audience, role of geotechnical engineers in earthquake hazard evaluation is very important. This cannot be done by structural engineers. They don't even understand what really happens below the ground. They take your the allowable bearing capacity, that is the number for them. But we need to do many things. We need to understand the dynamic characteristics of the soil and foundations and even the slope stability. So why need seismic zonation? So we have one nation. Why not use that? No, I will show you. That helps to identify vulnerable regions. That's all. But what we require is a necessary input to the earthquake resistant design. We need to do this zonation much more smaller scale. That's where seismic macrozonation plays. So let me take you through our second book in the Springer on the difference.
Professor Sitaram, is it possible to summarize or whatever?
Yeah, 5 minutes.
Yeah. Okay, thank you. I'm
aware of the time.
Okay,
so
thank you.
I'm going to conclude.
Thank you. Yeah.
So the micro level, meso level, macro level, seismic hazard at the bedrock level, what is the scale at which we have given all these recommendations. One can see this, and approaches and grid size recommended for micro, meso are also given very clearly, and what kind of testing we have to do also has been given. So many of these works based on methodology of shear wave velocity and SPT, and also we have calculated for many cities. And for the study regions of region-specific GMPEs are very, very key, as I highlighted earlier. And probabilistic seismic zonation maps are also very important in many of the nuclear power structures we have involved, and we have given very close. So we have done from small scale to very large scale zonation approaches ourselves, taking in the soil effects. So using the digital elevation models of the data, and all that is covered. And similar approach for the, as I told you, small scale to large scale estate like Sikkim to Karnataka, and also the country we have done. And all of that is covered in many of our books. We are also bringing out the geotechnical earthquake engineering in 2010 and through IGI Global. So I think many of you are familiar. We only bring 2 issues. So let me bring you to my last topic, time frequency analysis in next studies. So we thought that, in the response spectrum method, we only have the amplitude versus time, but the frequency is missing. So we need, there is an important study of that. So Ramakrishnan had adopted a Geber transform, which uses a Gaussian window function, which has a good control over the frequency resolution. That's the key. And and spectral leakage to analyze the generate the synthetic ground motions. So we generated approach was used to synthesize the ground motion for Japan and many of the Himalayan regions with the data, because the data should be available here. It's a data-driven approach. So some of these, this is what I call them as a physiogram. The last bottom right-hand corner is a physiogram. What you see, what you are all structural engineers are familiar, amplitude versus frequency plot, and or the seismologists are familiar, acceleration time history, what has been measured. And the other one is the frequency time, okay, what we call spectrogram and a Gaussian window. The last one is called physiogram, which is three-dimensional, where amplitude, time, and frequency are all represented on the same plot. So we have our recent paper on that for the Northeast Himalaya and and also the North Central Himalaya. So we have generated the spectrum. So a comparison of the analysis, it really gives you much better effect to observe the frequency content of the signals compared very well. So like we are involved in many of the design of geotechnical structures in my consulting work, whether it is slope stability, seismic design of foundations, earth dams, retaining walls, shallow foundations, geotechnical structures. So my list of companies, thanks to all of them for giving this opportunity, very large number of them are there, not listed, whether it is tailing dam design for all these seismic and or the pile design, shallow, closer to plain strain finite element also my students have worked out. So many large quantity of work at understanding the seismic design has come out for the geotechnical structures through our study over a period of 25 years. So recently we have also looked at the geosynthetic inclusions in the materials and how they have influences under dynamic loads. So we have also tried using geosynthetic applications, geogrades, geocells, geomembranes, and this is one of the other, my classical work is for the last 15 years I'm involved in the design of, I'm very happy to tell you today, this update is the arch is coming up, superstructure. But our job is the ground improvement. I'll just show you in a little while. This is the place where we have converted, put the foundation for the arch, slope stabilization work. The excavation is 6.1 lakh cubic meter, rock bolting is 33,000, shotcreting. This is one of the highest elevated bridge, going to be railway bridge in the world once it is constructed. So we are maybe a year away, in 1 year it will be ready. So that will give connection to Jammu and Kashmir from the mainland. So these are the kind of rock bolts, about 124 meters. This is on the right bank. And other related projects, I would have worked for ISRO, foundations of these large, very, very precise instruments, vibration isolation of buildings housed with sensitive equipment for SAC. And 32-meter diameter antenna at Nazafgarh, New Delhi for Indian astronomical observatories. And we have also worked for rice polishing machine equipment, BULA, granular dynamic simulation using discrete modeling. So dynamic stability of compacted sandfill in nuclear PFBR at IGCAR and shockwave assisted fracturing. This is one of the startup company with ONGC. We have worked on wave frac technologies private limited. So the geotechnical investigations, I will not take much time. So a lot of studies we started in as early as 95, as I told you, look at the laboratory axial experimental liquefaction, and where we measure the dynamic properties like shear, the dumping, as well as the shear modulus on many Indian soils. The first attempts, whether it is Bhuj, Ahmedabad, Assam, science were done, and the limitations of understanding the limitation of triaxial equipment. We have also gone into very high-ended high-ended testing systems at Institute of Science. Now we have resonant column and many other things are there. But I have also taken up on the discrete modeling approach, where we looked at the soil liquefaction from the particulate mechanics modeling as well. So where we try to compare how to understand the micromechanically, what happens to the structure when it is liquefied. So we looked at very, very carefully, and a lot of publications available. So what we try to look at, whether it is earthquake intensity, water table, soil type, gradation, drainage condition, confining pressure, relative density, all we have considered in different problems of whether it is slope instability, failure of earth structures, or tipping of buildings. And these are some of the work where we introduced mitigation of liquefaction by using the geosynthetics. Here we have put the biaxial geogrid in the discrete particulate simulation and try to understand in an elemental test how this is much more better. Now we are also working on air injection into the ground of saturated sand to reduce or mitigate the liquefaction. So there are some of the other works on AI, artificial intelligence tool techniques. Study predominantly use the SPT and the artificial neural network and support vector machine data on our experimental data, which we carried out from different agencies, or sorry, different techniques. And then already has done a lot of work on effect of fine sun pore pressure. And then Professor Das has done a lot of fantastic work on dynamic behavior of soils using Traxel testing. So this is my very recent work with Dr. Vivek on shock and blast loading behavior of granular material. The book also has come up in Springer. Some of you are interested, where we are look at how the shock waves in creation of these, subsurface sand ejecta. You can see that very clearly. We have done both experimental and numerical work here. A lot of fantastic work using the shock tape facility was used to generate planar shock wave, further facilitate the optimize, dissimulate the properties of rock. So let me come to the earthquake preparedness. This is what I was telling you last my slide. Earthquake readiness index tool for India has been developed to assess, thanks to Dr. Srivalsa. He has collected data for Delhi and regions in southern India. The chapter 4 of this book actually talks about the earthquake readiness index, which will be a very good tool so that we can prepare guidelines for households, schools, and business organizations, make them aware, prepare their community at level. So these are some of the data that we collected. Proposed tool assisted to give better idea on the levels of preparedness and identify the areas where people lack awareness. So we can identify, increase the awareness. So some of the instruments what we have called, even now we have put a broadband sensor at Indian Institute of Science at rock site where we're monitoring. We have put borehole sensor at 15-20 meters below the ground and measured earthquakes. So a lot of instrumentation work. And as I told you, cyclic Traxel, piezo vibrocone, thanks to many of my students, shake table study, development. All these developments are also done indigenously within India for our research work, very, very in the beginning of the work. So coming to the outreach activities, as I told you, journal, which is now an open access journal, and which is a fantastic one. And we are also bringing out Springer Transaction Civil Environmental Engineering. I am the editor-in-chief. So continuous efforts are made to propagate the idea of the geotechnical earthquake engineering. Geotechnical considerations are very crucial in the successful design of any part of the built environment. There is a strong need to raise awareness on the importance of the application of geotechnical skills and knowledge in every aspect of building developments. Geotechnical earthquake engineering will involve the review of the following: geological, seismological, geotechnical context of the development site, specific investigation and gathering of geotechnical and related data, development of geotechnical design parameters appropriate to the building development, due account of geotechnical consideration in the design of the building. Ground improvement is very key. Due consideration of the factors like overall land stability before the issue of the resource and building concerns. Review of geotechnical condition, modification of design details are necessary during construction. So roadmap to seismic safety, according to me, with a vision of zero tolerance to avoidable deaths due to earthquakes, significant contributions were made in the field of geotechnical earthquake engineering, which helped revamp the perception towards earthquake studies and the need for better design and preparedness in the country. So community awareness and preparedness is the key. Legal framework definitely is required, technical competence, professional ambience, enforcement by authorities is also, all of them are required, but R&D takes us to a new level and innovations have to happen in this area. So I also invite you to the 7th conference on recent advances in geotechnical earthquake engineering and soil dynamics, which is going to happen now because of the COVID-19, 12 to 15 July in 2021. It will be an online one. Please note all the proceedings have come out. Soon we will release them in 5 volumes. These are the contributory papers. There are more than 30 keynote papers which are getting ready. I welcome all of you to this conference. I think the last date of submission of paper, if there is anybody who would like to even now contribute, please contact us. We will see whether we can accommodate, but we request all of you to join for this conference between 12th and 15th of July 2021, supposed to be held at Indian Institute of Science, Bangalore, but now it is going to be online. So I thank all my teachers, all my students who have really worked very hard, toiled, and my institute where 27 years, right now I am sitting at Indian Institute of Technology, Guwahati, which was my first slide. The picture of the institute was in the first slide. My last slide is my parent organization, Indian Institute of Science, where I did my master's as well as my 27 years of career. And I like to thank all my collaborators and research fellows, all funding agencies, and in particular, Indian Geotechnical Society. And also, I would like to thank Indian Society for Earthquake Technology, for which I'm presently the president. So thank you all. Namaskar. Thank you for this opportunity. Bye.
Thank you, Professor Sitaram, for a very, very brilliant lecture. We know that it's your contributions in the area of earthquake, geotechnical earthquake engineering, quite exhaustive. We know it's not possible. Now I say there are no questions on this. We have a lot of questions, but I think they can directly contact you. And I now request Professor J.T. Sahu to conduct the proceedings. Thank you, Professor Sitaram. Oh, mute on, mute on.
I thank Professor T.G. Sitaram for presenting excellent IGS Annual Lecture. I also thank Professor Satyanarayan Reddy, Chairman Organizing Committee, IGC 2020, and his organizing team for making all necessary arrangements for this annual general session. Thank you very much.